Alkenes are more reactive than alkanes in addition reactions because the pi bond has electron density above and below the plane of the atoms that electrophiles can reach, and converting a weaker pi bond into two stronger sigma bonds is energetically favorable. Think of a pi bond like a loose rope above and below two atoms that holds extra electrons in a place easy to touch, while a sigma bond is like a tight, strong handshake right between the atoms. Electrophiles are positively charged or electron-seeking species that can reach the pi electrons easily because they stick out. So they attack alkenes more readily than alkanes, which only have sigma bonds tucked tightly between atoms. Breaking a pi bond and forming new sigma bonds usually releases energy or lowers the overall energy of the system, so the reaction pathway is more accessible. Also, the geometry of the double bond places the electrons where reacting partners can approach without having to distort the whole molecule much. A common misconception is that breaking any bond always costs a lot of energy, so students think addition should be unfavorable. But with alkenes, the energy released by forming two new sigma bonds often outweighs the energy needed to break the pi bond, so the net reaction can be favorable. Remember to compare bond energies rather than just thinking breaking equals bad. Another mistake is forgetting that the pi electrons are more exposed and thus more nucleophilic than sigma electrons. So students sometimes expect alkanes to react the same way, but alkanes lack that accessible electron density, so they do not undergo simple addition. Focus on where the electrons are located. A third error is assuming all additions happen the same way. Many additions proceed through intermediate carbocations or bridged ions, and their stability affects the outcome. So think about which intermediates are easiest to form. For more videos and resources on why alkenes behave this way and how to predict addition reactions, visit www.gumballdegree.com.